All right, welcome to CIE 101. My name is Claude Junkins. I'm going to be your instructor this semester for civil engineering graphics. I did teach this class last year, paid attention to some of the student comments, and going to make a few adjustments this year in that we are going to spend a little bit more time on the graphics and a little less on the building construction technology portion of it, as far as the nuts and bolts of construction and concrete. We'll hit on some of these, but a little lighter than I did last year. Um, and and of course, this class is split up between a live lab where you'll meet once a week to do some active drafting and modeling, and we're going to also have a lecture online. Following this, there'll be a number of lectures online that you'll be required to watch, and there'll be some quizzes on these subjects. But it's pretty much going to pertain to technical drawing, modeling, and aspects of creating graphic images that are applicable to civil engineering and other types of engineering also. I always like to start out with this slide that it shows some old prehistoric cave paintings, and I like to think that before there were written words, there were pictograms on the walls of these caves that people used to exchange ideas and news and gossip, how the hunt's going and what the animals are out there, and I the saying that a picture's worth 1,000 words certainly rings true with me. Some people I've heard the term coined graphic dyslexia, where being able to picture something in your mind and being able to transfer it to paper to express to somebody else is somewhat of it's difficult for some people, it's less difficult for others, and it requires some imagination and some practice, basically, to stay in tune with the graphic aspects of the drawing world. Hopefully horses didn't look that big back in the olden days, but somebody wanted to express that the animal they got was quite large. So again, we look at these pictograms, and they have, this one would be one that I would refer to as kind of a little bit out of scale. And we're going to be talking this semester not only about the graphics themselves, but scales, and how we layer these things together. A very long time ago, or I shouldn't say very long, not long ago, but prior to computers, which really wasn't that long ago, when I graduated from college, technical college, and as a draftsperson, we had not developed. Computers were just starting to come out with things like AutoCAD and MicroStation and some of these other CAD programs. And when I graduated, they were going to implement computers the next year, and that was in 1979. So it wasn't that long ago, and at least in my mind. Things have progressed rapidly since then, since the early days of the drafting on the board. We used to have to create blueprints, and we would take translucent paper and draw a floor plan on it. And if you wanted to add the HVAC work, you would add another, you would print it out on another piece of translucent paper and then draw your HVAC equipment on top of that. If you wanted to do an electrical plan or a plumbing plan, you would do the same thing and make these what they called sepia prints. So we ended up with a very paper-wise, paper hog. We just used a lot of paper, so it was rather labor-intensive. And we'll get into those things, because now instead of layers, we have layers on the computer that we can use, and we think of those as sheets of paper. We can also look back at our junior high days when we talked about number lines and being able to use coordinates. If we think about a two-dimensional drawing, what we're talking about is those two dimensions are x coordinates and y coordinates. If I were to look at the image of this person's face, and we have a square rectangular shape around this face, and we put an XY coordinate graph. We've all graphed things out. We can pick out points around the perimeter of this face and some of the highlights and assign XY coordinates to those objects. This is what we refer to as vector graphics. In other words, vectors referring to XY coordinates. If I were to move forward and actually trace these lines out and then remove the person's image from the square, we have a reasonable resemblance of that person's face. And if we looked at this point right here, that would be at approximately X at 2.75 and Y at maybe 4. So it has, each point on this line has an XY coordinate. There can be a million points. The more points you have, the more accurate the drawing will look. So you can make it as simple or as accurate as possible, and depending on how big the output is going to be, would have a significant impact. So this is two-dimensional drafting, drawing on the screen, representing a three-dimensional object. Let's throw in that third axis. We have an X and a Y for the 2D, and they're actually in this plane here. And we have a Z-axis for this depth, and we turn that person's face sideways. Again, we can trace the outline of that face, put it into the screen, remove the face, and we end up with a reasonable outline of that person's face. Again, with Z, this would actually be our Y-axis here, because X is actually coming towards us. In this axis, we'd have an X-axis there. So in this axis, we would have a Z and a Y-axis. Now, in our next view, let's put these all together. We can put this inside a cube. You may have already had this information, I'm sure, if you've taken any drafting in high school or other technology type aspects of drafting. We talk about this as the drawing cube, and it has 8 planes of projection. It has a front, a right side, a left side, a back, a top, and a bottom. Did I say 8? I meant 6. 1, 2, 3, 4, 5, 6. And then if we were to put that person's head inside that drawing cube, and we extend those images that we just traced onto the cube, this is referred to as the plane of projection. It's, in other words, taking this 3D element, finding where that element hits the plane of projection, and tracing it out. So we can think of these as translucent sheets of paper that are transposing that person's image accurately to full scale onto those planes. Now we can think about this as a sheet of paper, or we can think about it as a two-dimensional screen on your computer. We unfortunately don't, we can have 3D glasses, but we don't really have three-dimensional, we don't have the ability to step inside our models. So we have to train our minds to think about things as a two-dimensional image. Even if turning it in this direction, we're looking at this in a two-dimensional image, we're just seeing some isometric or orthographic, basically this is an isometric view kind of, with a little bit of perspective that gives us the simulation that we're looking at a 3D object. And then we can take a look at this and we can actually spin it around. This is a PDF 3D model, so we can actually look at the cube now on the computer from different, ooh, isn't there much of a brain in there? It's kind of hollow in the middle. So we can pull this around and we'd be able to pull these images to either side, but now we can look at this and with the computer we can turn lights on and off and change the shading, and if I wanted to see it in a different, you can kind of play around with these. Are kind of cool. There's an illustration that just shows the head without any colors on it. Shaded illustration and the solid. So it's kind of cool to play around with this stuff now, and it makes it so easy for us to do it on the computer. Now, in order to draw things correctly on the computer, and even on a drafting board, we used to carry 4 or 5 or 6 different pencil thicknesses or softness. You can see over here we have, these are actually, there's your 2H pencil and an H. The higher up you go on this, the softer the lead becomes and the darker the line. And if you get down into this, we'd have something on this 0.05 line weight. We might use something like a 6H pencil, which is very hard lead. You rarely have to sharpen it, and it makes very fine, thin lines, almost indistinguishable on the paper. And that's what we would use for what we call our construction lines or our temporary lines. As we get down here, the softer the lead, the more often you have to sharpen it, and to keep your lead even on the paper. But you can see some of these line weights get pretty thick, and we'll utilize this on the computer to show definition and show the importance of objects. The thicker the line, the more it is on the plane of projection and visible. If things show up on the plane of projection but they're kind of in the background, we would make those lines thinner. If we're talking about dimensions or notes, things that are important on the drawing but not necessarily the highlight, we would show those later. So our drawings become much more professional looking. We're not just slapping lines on. We actually have a reason to put our lines on in a certain line weight, in a darkness. And we'll work with that on the computer as well as maybe some simple drawing exercises with the pencil to start out with. But as we get our computers up and running with the AutoCAD software and the Revit software, we'll be utilizing those line weights to make our drawings look professional, consistent, and easy to read. And that's the key to this class, is making sure that the things we put out are consistent, look professional, are easy to read. And some of the things that we're going to be looking at this semester are making sure that when we put notes on a drawing, all of the notes are in the same font, they're in the same line weight, they're in the same layer on the computer, and they look consistent. So when you see one note, you know that the other note is just as important, but because it's in the same line weight. Now, if I had something I really wanted to make stand out to you, we may do it a little bolder, but we'd stay with the same font, the font size. You'll see as we move through the semester that this just makes the drawing so much more professional looking, and we'll look at some examples as we move through also. This is our United States National CAD Standards, version 5. Yes, we actually have National CAD Standards. And they give us plotted line widths in millimeters and inches for extra fine through quadruple X wide. And some of these things you can pull up and find them online, but we can kind of create our own standards too that kind of follow this guideline, but it's not something that we need to be too obsessed with, but we will kind of follow it to a certain extent. You can see here we have different line types. And this is from one of the textbooks we've used in the past. I haven't made you purchase it this year because we're going to get more into the computer stuff and a little less into the actual hand drafting work. But we still use some of these things as principles for our drafting work. Here's a center line. Here's a visible line with some thickness. A hidden line is just dashes with small dots in them. 1/8 inch dashes, 1/32 inch gaps. Do we need to be exactly there? Not exactly, but we want to use that as a guideline. Here's a cutting plane line, very thick. Anytime you're cutting through an object, like you can see, here's a cutting plane line that wants to cut through the end of this arm, and this is the actual section through that arm, so it shows a visible cut as to what the shape of that arm is if we were to turn it 90 degrees through that cut. These cross hatches, or these hatches I should say, have a certain line thickness. And you can see, I don't want to zoom in on this too much, but you can see the line thickness. Here's an upright position, which shows that this arm can travel vertically 90 degrees at least. Shows the moment of travel, or there's a chain line that goes on here that would be fairly thin and show something that's not in the drawing but shows where it would fall on the line itself. The outside lines are fairly thick. Anything incidental like this recess in the back, you can see this is something I can't see in the drawing, but there is a line in the background that's going to show up as a hidden line, 3 millimeters. Here it looks like it's hollow on the inside, so they've cut through it here. There's our cut line, or our break line, you can see is pretty thick, meaning somebody's kind of made it look so we can look inside that object and see what it is on this front profile. Again, you'll notice all of the text for the notes, all the arrowheads and leaders are the same thickness. The dimensions are all similar, so it gives you that professional engineering look. And it doesn't matter whether we're talking mechanical, whether we're talking civil, architectural, structural. We all use the same type of line weights and sections. This could be a property line in civil. In this case, it's a chain line because it's more of a mechanical type drawing up here. Stitch lines. Sometimes if you can't fit everything on one sheet of paper, they used to put stitch lines so that you could stitch one piece of paper to the other so that it would still be visible. These are all things that we'll work on throughout the semester as we go through this. Now, you have access to AutoCAD software. We're going to be using AutoCAD 2015, Basic AutoCAD. We're also going to be using Revit 2014. You may ask, why aren't we using Revit 2015? There was a textbook we were using last semester that I thought was very good, and it was based on Revit 2014, and that's why I stuck with it this year, because I want to kind of keep that textbook in mind. It had some very cool stuff going on. When you get to this page, and you'll see it's under, you can just type in Autodesk down here at the bottom. It's http://www.autodesk.com/education/free software/all. And up here at the top, it says sign in. When you click on that, it's going to ask you if you have a login to use it. If you don't, it's going to ask you to set up an account with AutoCAD. And I would say, just so you feel good about it, you're not going to get a bunch of advertisements and things from Autodesk to speak of. You may get some stuff on AutoCAD 360 or Autodesk communities, but it doesn't sign you up for a bunch of junk mail. And once you've logged in, you're going to download the software, keeping in mind that it's going to give you an account number and a code. It'll email it to you once you've signed in. It will also show it to you on the screen. The software is large. Make sure you give yourself plenty of time to download the software. During our first class, I'll show you where these things are. We're going to and show you how to download it as opposed to installing it right from the website. It just sometimes, if you have a slower modem or a slower network connection or a little bit slower computer network card, it could lock up on you. So to me, it's better if you download the software onto your hard drive and then install it from there, and that way you've got everything in place, and it doesn't, if it has to wait for the software to catch up to it, sometimes it'll crash on you. So depending on your connection speed, I would recommend downloading the software to your hard drive and then installing it from there. Next, inevitably, we're going to have some students that have Macs, and I would just say that I've cut out one textbook and that you don't need to buy. So if you have a Mac, you'd really need Parallels Desktop 10 for Mac, which is the one that most of the students used last year. This is going to give you a Windows emulation program on your computer, on your Mac computer. It may run a little slower than a Windows computer, but for the things we're doing, we haven't noticed a big problem. They do offer AutoCAD for Mac, but what we found last year was that the toolbars are so different than what we see in the Windows version that, number one, it's very hard to teach, and it's very hard for you to follow along what I'm doing on the overhead screen or the screens in the classroom, because the tools are so much different. So what you really need to do if you are going to use a Mac is get the Parallels desktop. Most of the places I see it's like $80, but maybe something to use. I really don't see that many engineering offices out there that are using Mac computers in the engineering offices. There may be a few, but for the most part they're Windows based, and most of the engineering software seems to be Windows based. There are a lot of graphic programs out there for Macs, but I think from an engineering standpoint, not everybody, but a good portion of people have gone to the Windows-based programs for engineering. Now, I feel your pain. Up until a couple of years ago, I was a MicroStation user. Thought AutoCAD was just something out there, and I loved using MicroStation. I had to change. I didn't like it. I felt very uncomfortable using AutoCAD, but I get into it. I watched videos. I looked at books. I went through this. Actually, teaching this stuff actually opens my eyes to many of the things that are available in AutoCAD. So you get used to it, and nothing against Macs per se, but in this class it is a Windows-based software. So getting Parallels on your Mac is really important, and I would do this before I downloaded any of the software. The other thing is we're going to be working in scales, and some people pick up scales really quickly. Other people have a little bit more difficulty with scales, and I bring this picture of Horton Hears a Who, remember Horton finds a whole world living on a dust speck on a piece of clover, and when I see that, I think of scales and the scales of things, and little Cindy Lou Who sitting on that dust speck, and the whole world, and him being able to hear it. But scales are important. If we were drawing on a drafting board with paper, we have to think about our scales up front to determine how much of the object or the project we can fit on a sheet of paper, and sometimes it requires multiple sheets of paper. But on the computer, everything we draw in our models is in full scale. We draw, if it's 10 feet wide, we tell the computer that that screen is 10 feet wide or 10 miles wide. However big we want to make that screen in our imagination, we can make it that big. And we'll think about it that way. Even though we're looking at a small screen, we're actually drawing everything to full scale. A foot's a foot, a yard's a yard, a mile's a mile. Even metric works the same way. But when we get ready to put that out so that we have to print it to a piece of paper, and yes, we still have to print things to paper so that it can go out in the field. I know more and more people are using pen tablets. The pen tablets can bring up the drawing on the screen, and they can measure things using their pens, but they really haven't caught on yet to the point where we're eliminating paper altogether. We got to keep our paper mills up and running to a certain extent. So we're still printing prints out, and we need to be able to print those out so that they are out to a particular scale or ratio. When we look at scales, for instance, and we have two basic types of scale. We have an architect scale and we have an engineer scale or civil scale. The civil scale and engineering scale is in base 10. So everything is divided up in sections of 10 divisions. And an architect scale uses feet and inches, so we're more in incrementally left to right in sections of 12 eighths inches, 16th of an inch, 32nds of an inch, but we know we got 12 inches to a foot, and each of those inches can be broken down even further into 1/8 inches or 32nd inches, so we're working in fractions. We also have two different types of scales. We have fully divided scales and we have partially divided scales. And one of the things I recommended in the email I sent out prior to this was that you should pick up a 3-sided engineering scale and a 3-sided architect scale, so we can use that on our paper, so we can learn. We're going to have some exercises where we're going to need to scale line lengths and dimensions on the screen. We have, in a civil engineering scale that is base 10, it is fully divided. Everything is divided all the way across. In an architect scale, it's incrementally or only partially divided. So here we see an architect scale. You can see that the ends of this are set up in divisions on this side, and they're read from both directions. So sometimes they can get a little confusing. On this side of the scale, it's a 3/8 of an inch equals a foot. So from this point to this point would be 1 foot. This is actually, and then this would read, even though it says 14 here and 13, what it is it's a 3/4 inch equals a foot read from the other side. So this 13 and 14 are actually read on the 3/4 inch side, which is double the 3/8. So when we read it from this side, if I had a line that started right here on the 6 and went down and went halfway down this line, I'd read this as 6 feet 6 inches. So the 12 and the 13 will confuse you, but this is actually 5 read from the other direction, because 4 is here. So this would be 5 feet 0 inches if it went from the 0 to this line. If a line falls in between, what you do is you put the end of your line on one of these whole numbers so that the remainder falls within this range over here, and each of these would be 1 inch divisions. So there's 1, 2, 3, there's 3 inches, 4, 5, 6 inches, 7, 8, 9 inches, 10, 11, 12 inches. If we look down here on the bottom, we can see that this is an 1.5 inch scale. On the other end of this scale, we would see a 3 inch equals a foot scale. So now we see it a little bit larger. This is actually a distance of 1.5 inches, but on the scale, on the paper, it would say 1.5 inches equals 1 foot. So this entire length from 0 to here is 1 foot. There's 1 inch, 2 inches, 3 inches, and you can see in between these it's large enough so we can pick out 1/4 inches. So each of the little tiny segments on the line is 1/4 of an inch. So a distance from this line to here would be 1 foot 3 inches. Out here, even though that says 2, it's coming from the other end. This would be 2 feet 6 inches from here to here. So we can count these up and divide them. We also work on ratios. If we look down here at some common architectural scales, and this is what the 3-sided end view of your 3-sided scale would be, because a 3-sided triangular scale includes these scales on it. 3/32 of an inch equals a foot, 3/16 of an inch equals a foot, 1/8 inch equals a foot, 1/4 inch equals a foot, 1/2 inch equals a foot, etc., 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 up to 3 inches equals a foot. A common scale that we'd see on an architectural plan for a floor plan would be 1/4 inch equals 1 foot. Okay? Now, that's an easy one to work with because we can use a ratio. And if I was drawing this on a computer at full scale and we move our view into a sheet view, in other words, a sheet of paper with a viewport, and I want to print that viewport out on that sheet of paper at 1/4 inch equals a foot, what would be my ratio from full scale to 1/4 inch equals a foot? Now, there's a very simple way to think about this, is you can say, how many 1/4 inches are there in 1 foot? There are 48 1/4 inches in 1 foot, because there's 4 1/4 inches to an inch and 12 inches to a foot. 4 times 12 is 48. So if I use a ratio of 1 to 48 in bringing my new vision into that viewport, it will scale it down, and when I print that out, I actually print the paper at full scale, it will print it out already scaled to 1/4 inch equals a foot, and I would just put a little note down at the bottom. And we will work with this extensively throughout the semester. That's what we call a partially divided scale. So when you print that out, you'd be able to take your scale and put it on there, and if it said 2 feet, it's going to be 1/2 inch would equal 2 feet at 1/4 inch equals a foot. Now here's a fully divided engineering scale, which is can be read a multiple ways. You can see it has 10, 20, 30, 40, 50, and 60. It's only read in one direction, and it's fully divided, so you always put your line or whatever you're measuring on the 0. In a 1 to 10, a 10 scale, this is actually 1 inch from this point to this point is actually a 1 whole inch. If I have a line that measures to 12 divisions, and my paper said the scale is 1 inch equals 10 feet, if 1 inch equals 10 feet, then that line would equal 12 feet. But we can also use that same scale and say 1 inch equals 100 feet. And then we just add a 0 to it, and it becomes 120 feet. This is 100 feet, 110 feet, 120 feet. If we said 1 inch equals 1,000 feet, which we might find on a map, a very large scale map, then we say this is, there's 1,000 feet, there's 1,100, and there's 1,200 feet. So we can use the engineering scale for multiple different paper scales depending on what it says on the paper. You can also see that the distance here, they line up. So this would be I'm not sure what's on the other end, whether it's a 60 scale or a 10 scale, probably the 60 scale, but 1 inch would equal 60 divisions across here, whatever the scale is. And a metric scale is laid out pretty much the same way, 1 to 5, 1 to 50, 1 to 500, 1 to 10, but the distances here are in millimeters and centimeters. So this distance here from 0 to this distance is 5, it says 5 meters, but it would be actually a distance of 1 centimeter in between these lines. We won't get into it too much in metric, but again, it's another base 10, so it's very similar to the civil engineering scale, and it is fully divided. Here are some examples. I've actually photocopied these on 11 by 17 sheet of paper. So we have the 3 sides of it's a 50 scale, that's why it's showing up over there. So if we look from this end, starting at 50, we can see that if we line up the 1 inch mark here and here, we can see that there's 10, 20, 30, 40, and 50. So 1 inch equals 50 feet, 1 inch equals 500 feet, 1 inch equals 5,000 feet, could all be scaled from this side. So this one is read from this direction over, this one is read from this direction over, but they're fully divided. Here's your 20 scale. You'll notice the 20 scale is half the size, so rather than this being 1, this is 2. Their 40 scale, you can see that 1 inch equals a distance of 4, so that could be 400, 40, 4,000, 40,000, could be 4 million. Depends on what the paper says the scale is, but it's an easy way to scale these out in a base 10 format. Here's your 30 scale and your 60 scale. Your architect scale, people have a little bit more difficulty with. It's just a full scaled ruler on one side, 1 to 1. So this would be 1 inch equals 1 inch. Down here we have 3/16 of an inch equals a foot. And on this other end it reads 3/32 of an inch equals a foot, depending on what you can fit on the paper. These aren't used that much unless you're kind of in an odd situation and it's in between an 1/8 inch or a 1/4 inch. You can kind of use one of these. 1 inch equals a foot, so this distance from this point to this point would be 3 feet 6 inches. It actually measures 3.5 inches, but when 1 inch equals a foot, it becomes 3 foot 6 inches. Same on this end, you're going to read it from this end, so it starts right here with 0, 1, 2, 3, 4. This one reads from this end, so it's 0, 1, 2, 3, 4. The divisions in between here, you'll notice this goes from 12 to 14, so reading this from the half-inch scale, this would actually be your 13 foot mark. And down here at the bottom, we have 3/4 of an inch and 3/8 of an inch. They're opposites, so they line up, and then 3 inches and 1.5 inches. If we actually print these out in 11 by 17, we can hand them out and use them as scales. I prefer that you purchase some scales because it's the one thing that you'll never regret purchasing. They're relatively inexpensive. They're $4 or $5 a piece, and you'll use them throughout your engineering career. I still have scales that I used when I was in drafting college from 1979 and before. So they don't wear out unless you use them as drumsticks. And we don't do that just because a couple rules with scales: you don't use them as drumsticks, and don't use them as straight edges, because if you start rubbing a pencil along the edge of them, it starts to wear off the grid marks. So you always use a straight edge like a triangle or some other type of straight edge, and just use your scales for measuring. You'll find that they last much longer. So in the next video that we get together, we're going to be getting more into the software, and we'll doing some demonstrations and talking about scales. We'll publish these PDF files, or these PDF files, up onto the Blackboard site, so you can download those if you want and use them at your discretion. So this is our introductory video, and there'll be plenty more to come. So thank you much, and we will be talking to you soon. Thanks.